Hi, I'm Conrad Fischer, and I'm the Director of Educational Development at Nassau University Medical Center, and I'm the Chairman of Medicine for Kaplan Medical. And this is Physiology, and I am an excitable boy. Here it is, excitable tissues. And how do we manage our membrane potential? Nothing like living up to our full potential here. Now, this section can feel very challenging, which is to say difficult. It's short. The major thing is this. Potassium is a cation. 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 Positive charges. When positive charges leave a cell, what does that leave in the cell? If positive charges exit, that leaves the cell negative. Now you understand the whole chapter. Thank you, the end. Now, when potassium leaves, it leaves the intracellular membrane potential net negative. Under normal conditions, before depolarization, is the intracellular environment negative or positive? And it is net negative. It's net negative. That's the key to understanding this whole chapter. The key to understanding this chapter is there are two forces of gradients keeping things in the cell. One is the electrical forces. If the intracellular environment is net negative, does that keep potassium in the cell? Or does it push potassium out of the cell? If the intracellular environment is negative, that should keep the potassium in the cell. On the other hand, the concentration of potassium is much greater in the cell than outside the cell. So the concentration gradient would force potassium out. The electrical gradient keeps potassium in. Under regular, non-energy dependent conditions, will potassium leave the cell or stay in? Potassium would diffuse out of the cell. Out from means flux, flow, flowing from the cell. Potassium should be flowing from the cell. The normal conduction of potassium is out of the cell. The efflux of the soul is happiness, says Walt Whitman. And the efflux of the cell is potassium leaving. Electrical forces will keep it in. Concentration will push it out because there's more potassium in the cell than there is outside the cell. Concentration will force it out. Electrical will keep it in. Under normal conditions, potassium will be conducted out of the cell. The magnitude of conduction is G, symbolized as G. And the normal conduction of potassium is passive, not energy dependent. Not energy dependent. Passive doesn't mean it doesn't follow a gradient. It follows a gradient, but it doesn't split ATP. You split ATP to get it back in, because you have to overcome the concentration gradient. So in order to overcome a concentration gradient, you need energy. That's why sodium-potassium ATPase splits energy, because you need energy to go uphill against the concentration gradient. The concentration pushes it out. The natural efflux of conduction is potassium out. Repolarization against the gradient is energy dependent. Sodium potassium ATPase goes in. Normal conduction goes out. Why out? Because the concentration is greater in the cell of potassium than outside. Concentration gradient pushes it out. Sodium potassium ATPase pumps it in. It's not a pump out. It's a concentration gradient out. It's like skiing. The ski lift is energy dependent, going up the slope. But once you're at the top of the slope, it's passively conducted down. When potassium leaves the cell, it leaves the cell more negative or more positive? When potassium leaves the cell, will the cell end up being more negative or more positive? If positive forces leave the cell, it makes the intracellular environment more negative. Okay. The number of channels in conduction, membrane conduction, is based on the number of channels that are open. If channels are opening, there's more conductance. If channels are closing, there's less conductance. The rate of the conduction across a membrane depends on the number of open channels, and it depends on what the net forces are. And those net forces are a combination of electrical forces and concentration forces. The concentration forces push potassium out. Now, we have three different channels. Ungated channels, they're just holes. If it's just holes, it'll just go through based on concentration. Ungated channels go through entirely passively based on concentration. Voltage-gated channels will look at whether there is a positive or negative charge. Like chloride has a negative charge. Sodium and potassium has positive charges. Ligand-gated, ligand is a protein transporter. Ligand-gated is a protein transport channel. Okay. Now, may the torture begin. Who did I piss off to get this section, huh? At electrical forces that prevent diffusion. That means the inside of the cell is negative. The potassium is positive. The electrical forces prevent the diffusion of potassium down its concentration gradient by attraction electrically. So it's saying that electrical forces are keeping potassium in. The cell is negative, the potassium is positive, the electrical forces are keeping it in. Concentration forces are pushing it out. Okay. Now, these come into equilibrium. Concentration and electrical forces will come into equilibrium, and if they're in equilibrium, then there's going to be no net flow of that ion. All right. The major thing in this equation is to be able to tell the combination of electrical and concentration forces and its effect upon the cell. Now, what this is saying is that the net negative forces inside the cell are going to keep potassiums in. It's the same thing we just said. It's the same thing that we just said. Membrane potential, somewhere between -70 and -90.